Hello students, this is Mr. Bob. In this short video, I'm going to attempt to explain to you why we linearize datasets or attempt to linearize datasets, what the purpose is, and walk you through it with an example. And at the end of the video, for those of you who are doing the Pendulum Lab, I'm going to try and apply it and give you some hints on what path to follow with the Pendulum Lab. First, let me make sure we understand why we linearize datasets. Let me just say, first of all, I think it is a very useful skill. Personally, I think it's quite helpful to understand mathematical relationships in the way that linearizing requires you to do it. But the second reason also is that both the IB and AP curriculums strongly emphasize this skill. I often see test questions where basically the question is asking students to either how would you linearize a data set, or they actually ask you to walk through and linearize a data set, create a new data table, etc. So for all the reasons I mentioned, this is why it's important. This is why we're spending time on it and why I'm expecting you to be able to do it. Okay, so let's get into it. So let's say we have a relationship in physics, and these two quantities, quantity C and quantity D, and by the way, it's totally made up. All this data is totally made up. This is for the purpose of illustrating these points. We know, or we suspect, that D equals 2C squared. In other words, this is an equation that we think governs how quantity C and quantity D are related to each other. Now, what do we do in science? We always do experiments to back up our theoretical ideas, our hypotheses, to see if the results of the experiment support the data we collect, supports our ideas. And if it does, great. If it doesn't, then we have to revise our ideas. So let's say we have two students here. One student named Diego Valeri, the other student named Becky Sauerbrunn, and they both collect data about this phenomenon, C and D. And you can see the data sets right here that I have. So now the question is, how can we tell if these data sets support this theoretical equation? If the experiments that Diego did and that Becky did support or don't support the relationship? Well, one way to do it is to attempt to linearize the data sets. What do I mean by that? What I'm saying there is, in order to test if the data collected in each experiment obeys the equation on the left, we have to change these data sets somehow, manipulate them, so that the new data set, when it would be plotted, if it did obey this equation, it would plot in a straight line. And if it doesn't plot in a straight line, then we know that it doesn't obey this data set, or excuse me, it doesn't obey this equation. Okay, so let's make sure we understand a little bit further, and I've got this graphic here to help you maybe figure it out. And I've tried to color code this, so pay attention to the colors. So notice the equation for a line, which we all learned in sometime in our math career, is, at least the slope-intercept form, is y equals mx plus b. Okay, so notice how I've kind of aligned this and color-coded it. So if D equals 2C squared is a valid equation, and if these data sets support that, then notice if I plot not C on the x-axis, but notice in red here, if I were to plot C squared on the x-axis and D on the y-axis, then supposing these things do obey this relationship, I should get a pretty linear plot. Okay, so the first thing you have to do is you have to convert these data sets. So notice what I've done here. In table 3, I've taken table 1, and instead of plotting C, I have converted it to C squared. So 1 squared is 1, 2 squared is 4, etc., etc. And likewise, with Becky Sauerbrunn's data, I have taken that C column and I've made it C squared. Okay? All right, so let's see what happens when we actually plot these data tables. So here we go. Let's first unveil Diego Valeri's. So again, on the bottom, on the x-axis, I plotted C squared. On the y-axis, I plotted D. Now notice what happens here is I get something that does not look very linear. In fact, if you look at these data points, there's clearly something a little different going on here. So just a visual look can help us clue it in, but also probably more importantly, if we go back here, if this data set matches this equation, not only should this plot linearly, but also what should the slope of our best fit line be equal to? Well, if you look back here in this theoretical equation, the slope of our best fit line should be somewhere near the 2. Okay? If I look at the slope of this best fit line, what is its value? It's 0.345, nowhere near 2. Okay, orders of magnitude off. So what Diego Valeri would have to conclude is that the data he collected does not support this theoretical equation. In other words, his experiment doesn't really support this idea that D equals 2c squared. That would be a valid conclusion for Diego Valeri to come to. And that would be the only really valid conclusion that you could come to based on the data set and the manipulations we've done so far. Now let's take a look at how Becky Sauerbrun's graph shows up. Notice when I plot Becky Sauerbrun's data here in figure 2, notice not only do I get a nice, neat line with every data point pretty much almost exactly, or in this case exactly matching because I rigged the data this way. Also, look at the slope of the best fit line. The slope of the best fit line exactly matches the theoretical value. And so a logical conclusion, a well-supported conclusion for Becky Sauerbrun would be that her data set strongly supports this theoretical equation because of the linearization, the attempt to linearize yields these results. Okay, so that's the big idea with linearization. It helps us as scientists see if our data sets, to what degree our data sets match the theoretical results, the theoretical equations that are supposed to govern it. Okay, now let's turn our attention, for those of you who are working on the Pendulum Lab, let's turn our attention to that Pendulum Lab. If you look here, I have taken, if you remember the video that I made, if you go to minute 29, I give you some hints. I give you some hints in that slide about how you might take the equation for a simple pendulum and how you might manipulate it to get it into a form that then you can attempt to linearize the data you have. And notice there, I've given you 2 forms, okay? And again, I've tried to color code it. So the t, the period of the pendulum, could correspond with your y value. And some form of the length of the pendulum could correspond with your x values. And then your slope, the resulting slope, the expected slope, should conform with one of these 2 that's in green. Now I want to emphasize this is not the only way to linearize the simple pendulum data. There are other variations and permutations you could go to, and if you went some other route and you feel comfortable you can explain it, great. But these are the 2 most common ways that I've seen students accomplish this. So I think I'm going to stop there. I hope this is helpful to you. Again, as always, if you're still a little confused, struggling, please reach out to me and we can continue the conversation there. Thank you.